Okay, thank you very much, Chris, for the introduction. And you can hear me well, right? Can you hear me well? See that? Okay, perfect. Yeah, so thank you very much for the introduction and for inviting me to this beautiful conference. Um, so as Chris already told you, I'm going to tell you about my recent work with Davide Gaotto on Miura operator, and I'm going to give you a new interpretation of this important object in the theory of KDV hierarchies and vertex operator algebras known as Miura operator. And I'm going to actually argue that you can think about Miura operator as an operator living at the intersection of M2 brane with M5 brane in twisted M theory. And this is based on my research with Davide Gaotto that we published at the end of last year and some work in progress. Okay. So the talk nicely fits within the correspondence between geometry and representation. So let me just start with the following big picture. It is expected that branes or sheaves in toric-Calabi-Yau free folds are actually in correspondence with representation theory of affine Youngians. You can think, for example, about the famous AGT correspondence from 12 years ago as an example of such a correspondence. Because it relates the Virasoro algebra with U2 instantons living on C2. And you can think about Virasoro algebra as one of the representations of affine Youngian of GL1. And on the other hand, instantons on C2, it's quite, you can embed C2 inside C3, which is a toric-Calabi-Yau free fold. And it's very likely that, I mean, there's a relation between these two. And various other BPS CFT correspondences, as people like to call it, are also special examples of this geometry representation theory correspondence. But I prefer not to call it BPS CFT because, as we are going to see even in this talk, it's not always CFTs or their symmetry algebras known as W algebras that appear on the representation theory side. And today, in today's talk, we are actually going to restrict to a very simple class of Calabi-Yau free folds, which is just the flat space, just C3. Or more generally, I'm going to comment on generalization to ZK singularities. I'm not going to talk much about this example like in great detail, but many things, basically everything I'm going to say today generalizes very, very naturally into this C times Z2 more mod ZK case. You just need to basically like enhance everything into matrices. But anyway, let me start with the description of the geometry side. So the physics one should have in mind for the purpose of this talk is an M theory, which is an 11-dimensional theory. And I will put it on the product of C times C star times R times extra C3. For the purpose of this talk, I'm going to split the space-time into two parts. The C3 part that I want to think about as the Calabi-Yau free fold I'm interested in. And I want to somehow compactify on this part of the space-time. Okay, there's a way how to compactify on even non-compact spacetimes if they admit some torus action. And indeed, C3 does admit torus action because you can rotate for example, you can rotate the free coordinate lines, the three different C's inside C3, and turn on the deformation of the theory such that the theory effectively localizes to the fixed point of this torus action. And since the fixed point of the torus action here is simply origin, the origin, you effectively dimensionally reduce and to 5 dimensions in this case. So I will call this part of the space-time as the compact part. And the rest is a 5-dimensional part, C times cylinder times R, that I will call for the purpose of this talk as the non-compact part. Okay, and I will call the deformation that I introduced omega background, and depends on the free parameters associated to the free S1 actions on the free coordinates. And there are these parameters epsilon 2, epsilon 3 that parameterize this deformation. Okay, so according to the correspondence, different brain configurations in this geometry should lead to different representations. So let me now discuss a large class of brains that you can introduce in this geometry, such that you still preserve this torus action necessary for the omega background. So first, you can introduce M5 brains wrapping the cylinder and having three possible orientations in the compact part of the spacetime. Here, here, and here. Let me introduce multiplicities, which means I'm actually introducing N1 stack of N1 M5 brains with one orientation, and two M5 brains with another orientation, and M3 M5 brains with yet another orientation. This configuration was actually recently called by Nekrasov spiked instantons. So I will maybe going to call this configuration of M5 brain spiked instanton configurations. Anyway, furthermore, I'm going to introduce M2 brains, and again, they're going to wrap R in the 5-dimensional non-compact part of the spacetime. They're going to wrap one of the C's inside the compact Calabi-Yau threefold C3. And again, one can produce three different multiplicities for each of the orientation. The geometric picture has a very natural analog. If we exchange C3 by this ZK singularity, you can again turn on omega background, and you can introduce three different M5 brains of three different orientations and M2 brains of three different orientations, and study everything in the very same manner as we are going to do today. Okay. So now let me move to the representation theory side. So I told you that there should be a representation of some universal algebra associated to some affine again associated to each brain configuration. So let me tell you, why do we even expect some kind of algebras or representations to appear? Let me give you like this quick physical argument. So first, low energy dynamics of a brain is expected to be described by quantum mechanics living on its support. If you compactify on part of the support of the brain, the effective theory describing the brain is going to also dimensionally reduce to the effective theory living on the non-compact part of the spacetime. So in particular, in our case, in our configuration, if we compactify on the omega background, we're going to get an algebra of operators living on R from the M2 brains, because note from the previous slide that the M2 brains live on R in the non-compact part of the spacetime. And analogously, the M5 brains are going to lead an algebra of operators on living on the C star. This second algebra actually has a much richer structure of so-called vertex operator algebra if we keep track of the holomorphic dependence on the position on this C star. But this is not going to be very important for the purpose of our talk. So you can really think about both algebras as associative algebras. Okay, and it was realized in Kevin Costello that both the algebras that come from M2 brains and M5 brains actually need to satisfy some relations of a universal algebra that I call Y in order to admit non-anomalous coupling to the function of the M theory itself. And in our examples, where the Calabi-Yau threefold is simply C times C2 over ZK, the universal algebra is known as the affine Youngin of GLK. And this geometric representation theory picture then predicts an existence of a family of representations A, N1, N2, N3, and Y, N1, N2, N3, depending on free integral parameters for both the M5 brane and the M2 brane. And there should exist a representation of this algebra Y for each triple of the integral numbers N. So there should exist these maps that I write down here. Okay, so not only I'm going to tell you what these maps are and how to construct these algebras in this talk, but what we actually did with Davide, we investigated how those two interact. And we did it by looking at the configuration where the M5 branes and M2 branes intersect. So you have the M5 brane wrapping on the cylinder, wrapping the cylinder with the algebra of operators Y, N1, N2, N3. And you can pierce it with an M2 brane. So this is M5. This is the stack of M2s. And there's going to be an algebra A, N1, N2, N3. Algebra of operators living on the M2 brane. And then there's going to be some kind of operator you can insert here. And you can see that this operator L should actually admit an action of both the algebra A and the modes of the algebra Y, coming from bringing the operators living either on the cylinder or on the line towards the L. So you can see that by investigating these kind of intersections, you can actually learn something about the relation between these two representations. And this is what we are going to do in this talk. Okay, so let me start telling you what the M5 brane algebra is. So it has been known for quite some time and basically dates back to the work of Nakajima in 1995, and it was later interpreted by physicists. Many people contributed into the field. But basically, the simplest statement is that if you take a single M5 brane and an omega background, as we did on the slides, like a couple of slides back, these lead to the GL1 Katsumuri algebra living on the C star. So what is this algebra? If you are a physicist who knows some theory of vertex operator algebra, so for some string theory, you're probably used to dealing with operator product expansions. And here, the GL1 Katsumuri algebra is just an algebra generated by a single field J with the following operator product expansion that basically encodes the singular behavior of collator functions if you move two insertions of J together. And here I've introduced this normalization of the operator product expansion, where down here in denominator, there are epsilons that correspond to the support of the brane. Remember, we had like 3 different orientations along the 3 different combinations of the 2 C's, the different planes inside C3. And these just label the support of the M5 or the corresponding M5 brane. You can think about the very same algebra as an algebra of modes by basically Fourier transforming, doing Fourier transform along the circle, or I will sometimes draw the cylinder as a punctured plane, and then doing Laurent expansion. So you can basically think about the very same algebra as a universal enveloping algebra of the following algebra given by the following commutators, where n is arbitrary integral numbers. And as I told you, there should be 3 different algebras associated to the 3 different orientations of M5 brane, and you get them simply by permuting the parameters epsilon. That's how you can get the algebra that I call Y100, Y010, Y001. It might seem somehow trivial because now at this point, the algebras are really just the same ones. I just picked normalization differently. But we are going to get, if you start like fusing them later on and producing like more complicated algebras out of these simple ones, they actually fuse to something highly non-trivial. Okay, so the first statement is that according to Kevin Costello, all must be different representations of the GL1 affine Youngian. So let me just briefly tell you what the GL1 affine Youngian is. So it is an algebra generated by two generators that I denote as T20 and T02 for an arbitrary integral number. I'm going to tell you what the, you will see the reason for notation that I introduce here later on when moving to the M2 brain algebras, at least hopefully. But anyway, so we have these generators, and they satisfy a relatively complicated system of relations. I've decided not to write down the relations here because it would just take me 2 slides, and I think it's relatively complicated for a person who hasn't seen the relations before, and the person who has seen the relations already knows them. So I decided to skip and not show you the relations. And instead, I'm just going to tell you that this algebra Y indeed admits 3 different Fogg representations given by the following formula. So you just map the generator T0n into J, and T20 generator into the following combination. Okay, and you can do the very same thing with the M2 brain algebra. And it has been known for quite some time that M2 brain algebra in Nekrasov's omega background, placed in flat space in C times R geometry, leads to the Weil algebra living on R. You should also think about it, just to make a connection to Matthew Bullimore's talk a little bit. You can think about this algebra as the quantization of the algebra of functions living on Coulomb branch of this ADHM quiver. Or equivalently, yeah, anyway. So anyway, this algebra is generated by 2 generators, the derivative and Z, with the obvious commutation relation. And in order to get an algebra associated to M2 brain on C times C star over R, the only thing one needs to do is to add the generator 1 over to Z. The reason is that you can think about the derivative and Z as parameterizing the position of the M2 brain in this C times C directions. And the commutation relation is just quantizing these 2 coordinates. And if you're on a cylinder, you also need to allow the functions that are singular at the origin. If you look at a cylinder from the point of view of a punctured sphere, punctured plane, and it is natural that the extension should be just by this function 1 over C, and it satisfies the obvious relations, and leads to the full algebra that I denote as A1, 0, 0. And obviously, one can get an algebra associated to different orientations by simply permuting, like changing the epsilon 1 into epsilon 2 or epsilon 3. Okay, and again, Kevin predicted that all of those should be representations of the same affine Youngian. And indeed, it turns out that the algebra Y admits 3 different polynomial representations of this form. Okay, so let me now tell you about the. Let me now, after telling you what are the elementary representations are, before actually starting building up the more complicated ones, let me pause a little bit and tell you how to think about intersections. So I already draw this picture where we have the M5 brain, M2 brain piercing M5 brain. Sometimes, just for simplicity, I'm going to collapse the circle, compactify the circle, and draw pictures of the following form. And there is an operator that I denote as L living at the intersection. Oh no. Okay. And this operator should admit an action of the algebra A n1, n2, n3, since we can take local operator on the M5 brane and fuse it with the operator L. But it actually does admit two actions. You can act from the top and from the bottom. And similarly, you can act by pair of modes from the left and from the right of the modes of the M5 brane algebra Y, N1, N2, N3. And moreover, analogously to the requirement that the M2 brane and M5 brane algebra satisfies some relations of this universal affine Youngian, we expect that the consistency of the coupling of the intersection itself with the five-dimensional theory should also lead to some kind of constraints on this operator L. So there should be some constraint. And the constraint should somehow relay the actions of the two algebras A n1, n2, n3 and Y n1, n2, n3. Okay, and so what we did with Davide last year is that we identified this constraint, and let me just tell you how the constraint looks like. So we found out or proposed that the consistency of the coupling to the five-dimensional theory is governed by the coproduct structure of this universal algebra Y. So the coproduct is quite well known, written in the basis that we used. It's given by the following equations. So basically, both T20 and T0n map to the sum of the two generators in the two copies of Y. But the generator T20 actually receives a correction by this infinite sum, this tail connection. There's a question. I'm confused about the left and right actions. What's the codimension of the intersection? So the intersection is going to be one-dimensional, is zero-dimensional. So it is a point that intersects. I mean, so first, whenever I'm talking about these M2 brane and M5 brane operators, I look at it from the perspective of the compactified theory. So the theory on the 5 dimensions. Let me just go back a couple of slides. Right. So I'm restricting to this part of the space-time, and you can see that all of the none of the branes wrap the C here, so you can really forget about the C whenever I draw the diagrams. And here, when I draw the pictures, you can really think about this plane as being the C star, and this direction being the R. So from the perspective of this part of the space-time, you are at a point. They intersect at a point, and this M2 brane is one-dimensional, and the M5 brane is the M5 brane operator is dimensional. No, I think you cannot go around intersection. You always know what. With the operator, you cannot. Right, because it is not codependent. I mean, right. Yeah. Okay, so let me go back to the consistency condition. So I defined you this coproduct structure, and now I'm going to tell you how to write down the gauge invariance condition, and it's given by the following form. Okay, so I first start with any element T inside the universal algebra Y. I first map it by the coproduct into the tensor product of two copies of Y. And then I map it by these representation maps that I still haven't defined for arbitrary N1, N2, N3, but that's something we are going to do later on in this talk. And we can map it into N1, N2, N3 times A, N1, N2, N3, and act by the result from the left. You can do the same thing with the on the right. The only thing that I exchanged the order of A and Y, and the consistency condition is a requirement that L intertwines these actions. Okay, and it was actually checked recently, earlier this year, that these are indeed the correct constraints. It was checked earlier this year by performing actual perturbative analysis in the 5-dimensional theory. There are some questions, so let me just look into them. Is it because you're considering the algebra of modes for the observables on M5 brane? Yes, I was asking about the algebra. I mean, wrong. Okay, there's going some discussion in the chat. Right. So I think there's this confusion of of dealing with the mode algebra versus of the M5 branes versus the picture of local operator, that you can really go with the local operator around. I think that was kind of the confusion, I believe. So that's actually the reason why I compactify on this circle, because I want to think about the mode algebra as really everything as associative algebra. So I'm kind of compactifying, or I want to compactify on this circle and really view it as an intersection of two lines, where the most of the algebra of the M5 brane algebra live on the fat line on the picture on the right, and the most of the M2 brane algebra lives on the vertical line. And I'm not looking only at zero modes of the vertex operator algebra. I'm really looking at all the modes of the vertex operator algebra. Okay. So let me now tell you what is the Miura operator, how the Miura operator pops up, and why it should be associated to the intersection of M2 brane and M5 brane. And we're first going to do it for the case where the M2 brane and M5 brane completely intersect. So it means that they don't share any direction even in the compact part of the space-time. So I'm going to now tell you what is the operator L associated to the following configuration. But before doing that, let me restrict the general formula that I gave on the previous slide, or on the 2 slides back. to this situation where we have a single M2 brane and a single M5 brane. So this first I wrote down the coproduct again, and the only thing that I do, I really just plug in the representation maps that I wrote down earlier. Let me go back. Earlier here when I was talking about the M5 brane algebra. And where was it? And here when I was talking about the M2 brane algebra. Okay, so in particular, you can see this term is simply going to map to Jn. This term is going to map to this complicated looking combination. This guy is going to again map to Jn, just with negative indices. And analogously here, we are going to get the M2 brane algebra representation, which has the following form. And here we have this. Right. So I simply plugged in the representations. Okay, and then the gauge invariance condition reads as follows: that there should be an operator L that commutes with this sum of j and with z to the power of n over epsilon 1, and it should almost intertwine the sum of the t20 and the derivative up to this tail term that actually has interchanged indices, which is a slight technicality, but very important. Okay, so now I would like to argue that this condition is actually satisfied by the so-called Miura operator, introduced long time ago in the context of KDV hierarchies and later used in the context of W algebras. But for the purpose of this talk, we are going to think about this differential operator that I just wrote down here as an element inside a tensor product of y100 times a100. And obviously, it has a natural bimodular structure because you can multiply this expression from both left and right by the modes of the algebra, by the Jn modes, but also by the derivative and z. And you get again some kind of different pseudo-differential operator. So you can act on by both algebras from the left and from the right. And furthermore, you can sit down and check that this operator actually satisfies the consistency condition that I spelled out on the previous slide. It's a rather non-trivial calculation. I mean, 2 pages long maybe, but it actually turns out to work out. So this suggests that you can actually reinterpret this Miura operator as an operator living at the junction of these M2 brane and M5 branes. Right. So let me now tell you what happens if you have this quantitatively different configuration where the M2 brane and M5 brane share a direction inside this non-compact inside this compact part of the space-time. So let me now investigate the following configuration of branes. So this is quantitatively different configuration, since now the M2 brane can actually end on the M5 brane, and we can split the two endpoints. We can separate them. So we have an or like put it reversely. Like if we have two M2 branes ending from either from one side and from the other side on the M5 brane, we can fuse them together to produce an operator associated to the intersection. And that's a procedure that we are going to use to derive what the generalization of the Miura operator should be. Okay, A fact that has been known for quite some time in the AGT literature is the endpoints of M2 branes actually are associated with vertex operators for the vertex operator algebra. What we've checked with Davide that these actually also satisfy a version of the gauge invariance consistency condition, and it has the following form. You can really think about this consistency condition as being the very same condition as the one from the previous slide. Because what we have now, we have the M2 brane, sorry, M5 brane. We have the M2 brane, but it doesn't continue. So you can really think about the right-hand side here as T mapped by the coproduct composed with the trivial representation, where the trivial representation is associated with this non-existent M2 brane, times this Y1, 0, 0. And it just turns out that these operators exactly satisfy this gauge invariance condition. Okay, and using these operators, it's actually pretty easy to rederive the pseudo-differential Miura operators we found with Tomáš Procházka. They were actually quite surprising. We devoted maybe like 20 pages to these Miura operators and tried to pose them and play around as with the standard Miura operators. But here you can actually see that there exists their derivation that is just for lines long. So let me just go through that and tell you what the Miura operator to the corresponding configuration is. So as I told you, we are supposed to start with the two vertex operators, and we need to fuse them. So in the first step, I do the operator product expansion to express it as the following normally ordered expression. In the second step, that is slightly less trivial, I use a fact that the following map relating z to the n del to the alpha z to the m with the following ratio is actually an isomorphism of A100 bimodules, where on the left you can act by z and del from the both left and right, and on the right you can act by z tilde del tilde, and it turns out that these two actions are the same. This map is actually isomorphism of such bimodules. And using this expression, you can exchange this factor of z minus z tilde to some power by the derivative to the following power. And in the last step, the only thing I do, I commute derivative to the right by using the product rule for derivative, and get this pseudo-differential operator that we call pseudo-differential Miura operator, and use for constructing these more complicated vertex operator algebra that I'm going to talk about later on. You can see that this is a pseudo-differential operator containing infinitely many terms, and with all the terms here, with the coefficients being operators of the vertex operator algebra. And one can again sit down and check that this operator satisfies the correctly specialized gauge invariance consistency condition. So what we have done I've just told you how to construct 9 different elementary Miura operators associated to the 9 different configurations of M2 and M5 branes. In particular, the diagonal guys here are just the Miura operators of the standard type, the old ones, just with the parameters epsilon permuted. Whereas the off-diagonal ones, again, can be obtained from simply permuting the parameters epsilon in the expression that I gave on the previous slide. Okay, so let me now move to building up more complicated junctions by fusing or taking products of the Miura operators and defining what the algebras of general N1, N2, N3 are. Okay, so here what I do, I take an intersection of a single M2 brane with a copy of n different M5 branes, and I try to fuse them together. So at the level of Miura operators, this is nothing else but the taking product of multiple Miura operators. And this is actually the original purpose of the Miura operator, called the Miura transformation, that people in key hierarchies and W and algebra and vertex operator algebra literature use quite heavily. So let me go through the calculation. So here on the right-hand side, I take, as I told you, 2 copies of the Miura operator. For the first Miura operator, couples are Z and Z del algebra, this are M2 brane algebra, with the Jn modes. On the other one, since it's associated to the same M2 brane but a different M5 brane, it couples the same M2 brane algebra with a different M5 brane algebra. So I denote the generators of this different M2 brane algebra, M5 brane algebra as J tilde. So here I simply write down the 2 Miura operators, and I express it as an operator of the second order operator, differential operator in a standard form by commuting the derivatives to the right. So here, for example, the product of these 2 derivatives gives the second derivative, and analogously you reproduce all the other terms. The only thing that I should be careful about is the commutation of the derivative with the J tilde current, producing this term, but also producing the derivative term here. Anyway, what one gets turns out to be a pseudo-differential operator with some coefficients, and these coefficients, J plus J tilde, and JJ tilde plus derivative of J tilde, actually turns out to generate a subalgebra in the tensor product of 2 GL1 smoothie algebras. And this subalgebra is known as the Virasoro algebra times GL1 hat. You can do the very same construction with for arbitrary n and recover these more general Wn algebra generalizing the Virasoro algebra. And this is actually, at least for me, probably the simplest construction of Wn algebras, and also one of the original purposes of the Miura transformation. Okay, and one can again check that the fused algebra, a fused Miura operator, satisfies the following gauge invariance condition, where now I need to tell you what the algebra Y00n is. It is nothing else but the following. So what you're supposed to do to get in order to get the T20 and T0n in this representation Y00n, one first uses the coproduct n-1 times, which gives you an element inside product of inside the tensor product of n copies of the universal algebra Y. And then you map each of them by the elementary representation Y00N. As a result, you're going to get an element in the tensor product of N001 elementary representations. And this is yet another construction of the WN algebra. And you can use this representation in the gauge invariance condition and check that the product of the Miura operators intertwines the corresponding actions of the two different algebras. And one can do the very same thing with these more complicated generalized pseudo-differential Miura operators. You can just multiply them. You can identify these more complicated generators of the more complicated so-called corner vertex operator algebras as coefficients in front of the pseudo-differential operators that you get from the commutation of the differentials to the right. And you can also show that it satisfies the gauge invariance condition of the corner vertex operator algebra yn1, n2, n3 analogous to the WN algebras, where now yn1, yn1, n2, n3 algebra is defined in a very similar way by using the coproduct n1 plus n2 plus n3 times, and composing with n1 copies of the elementary representation of type 1, n2 copies of elementary representation of type 2, and n3 copies of the elementary representation of type 3. Okay, so now I told you how to compose the Miura operators in this direction of R by introducing multiple M2-M5 branes. What I'm going to do next, I'm going to tell you that you can actually use the very same Miura operator to start playing around the fusions of multiple M2 branes. So the picture to have in mind is a bunch of M2 branes intersecting M5 brane at n different points and fusing them together. And this was actually the motivating example for the whole project. It was the following observation: that if you compose the two Miura operators here, but compared to the previous story, I'm doing a slightly different composition. I have again the two Miura operators, but this one pairs again the M2 brane algebra with the M5 brane algebra. But this one now couples the same M5 brane algebra because we have the same M5 brane, but a different M2 brane. So I denote the algebra associated to the other M2 brane with the tilde. And here I just write down the Miura operator. Again, I can use the same kind of an analogous construction by taking normal ordered product, by expressing everything in terms of normally ordered expressions on the vertex operator algebra side. One gets the following expression, where from the normal ordering of these z, j tilde terms, one actually picks some extra contribution that contributes by the following function. And it turns out, I mean, as pointed out by Tomáš Procházka, this combination here looks very similar to the Kalugier-Moser Hamiltonian. In turn, it turns out that the Kalugier-Moser Hamiltonians are known to be generators of so-called spherical Chladnick algebra in Dunkler realization. And the question was, can we actually make the connection more precise? And is there a free parametric generalization of the Chladnick algebras? And the answer of both questions is yes. And that's something that I'm going to do in the rest of the talk. So let us use this very same coproduct formula that we used for constructing these more general I-brane algebras, these corner vertex operator algebras, but now for these M2 brane algebras. So you can see that the T0n generators simply map to the sum of the two z to the n generators. The T20 algebra maps again to the sum of the two derivatives up to this tail term, coupling the z and z tilde generators. Well, you can actually resum this infinite sum to obtain an expression of the following form. And what you recover is nothing else but the Gaussian-Moser Hamiltonian and the Dunkel realization of the spherical Chernigg algebra A002. And we recover it from the very same coproduct as we did for the M5 brane vertex operator algebras. And again, nothing stops us here, and we can use the coproduct to assemble a free parametric family of these spherical Chernigg algebras by again applying the coproduct n1 plus n2 plus n3 minus 1 times and composing with n copies of A100 representation, n2 copies of the M2 brane representation of the second time, and n3 copies of the M2 brane representation of the type. One can again resum all the terms that one gets and obtain the following expressions, generalizing a quite well-known two-parametric family, first discovered, I believe, by Sergeyev and Veselov, and later on studied by other people. So the original one, the two-parametric family, is the one that would correspond to these terms. And as you can see from this construction of the coproduct, these terms can be actually extended by these extra terms that I haven't circled to obtain a free parametric family. And you can see, you can actually discover a triality in these Chernigg algebras. And right. Okay, and analogously to the previous discussion, it is straightforward to check that one can compose the Miura operators of the three different types. And they do satisfy the gauge invariance condition for the A, N1, N2, N3, intersecting Y0, 0, 1. And the whole story has actually matrix generalization. You can just basically lift everything into matrices. That is associated to the geometry of C times C squared over ZK. The universal algebra Y is that was generated by these generators T20 and T0n, becomes now algebra known as GLK affine Yangian, generated by EIJ0n and T20, where I and J goes from 1 to K. So you can really think about the generators again as being promoted to matrices. And the algebra Y again admit three different elementary M2 brane representations, where E's here are some particular representations of the GLK Lie algebra, depending on alpha being 1, 2, 3, corresponding to the three different orientations one can introduce. It is known also that the algebra Y again admits three different elementary M5 brane representations. Furthermore, the coproduct formulas naturally generalize to this case. And this all leads to a free parametric family of N2 brane algebras and M5 brane algebras that include, for example, the spin Gaussian-Moser system and its various generalizations. And the two families of algebras again interact via matrix generalization of the Miura operator and vertex operators for Kac-Moody algebras that are not GL1, but Kac-Moody algebras associated to more complicated Lie algebras. Okay, so let me finish with the conclusion. Today I told you that the Miura operators are operators that can be given an interpretation of an operator living at a junction of M2 and M5 brane in twisted M theory. They satisfy these R matrix-like gauge invariance conditions. And the coproduct of the affine Youngian of GL1 can be used to define a free-parametric family of corner vertex operator algebras that I denote as Y, N1, N2, N3, but also a free-parametric family of Cherednik algebras, A, N1, N2, N3. Furthermore, the Miura operators can be fused together to describe junctions between more complicated M2 and M5 intersections, and they relate those more complicated algebras. So in particular, this composition of the composition of Miura operators is consistent with the coproduct of the two algebras acting from the right and from the left. And finally, something I didn't have time to talk about very much, the screening charges and pseudo-differential operators, Miura operators, and the complicated structure of degenerate representations of the corresponding vertex operator algebras seem to quite naturally emerge from the current picture. Okay, thank you very much for listening. And if there are any questions, I would be more than happy to answer them.
Thank you very much. Thank you for a nice talk. Does anyone have any questions? I have a somewhat vague question, which is presumably this setup that you described makes sense on where you talked about maybe the products of the affine line and a surface singularity. Presumably you could put any toric threefolds in this construction. I don't know if there are other interesting examples. Sort of a question.
Right. So I believe that, so physically, like you should be able to exchange the C3 that I was talking about by arbitrary toric Calabi-Yau threefold, and presumably the whole story should somehow generalize. I just don't know how exactly. And furthermore, you can also start playing around with the non-compact directions. Sorry, that's right, with the non-compact directions, and right, exchange the C times C star by other geometries, leading again to different modifications of the story. For example, if you exchange C star, the C times C star by C star times C star, I expect that the corresponding setup to be related to the quantum toroidal algebra, because what you need to do at the level of, for example, M2 brane algebras, you need to invert also the derivative. So you need to like somehow double the number of generators, and now you actually have the S and T transformation, the torus transformation that act on the two different cylinders, and so on. So you can consider like more complicated geometries here as well. Yeah, so I mean, there are many possible generalizations. Yeah.
Very interesting. Thanks. Does anyone else have a question? Okay. Well, if not,